deep in the vast expanse of space, in a serene corner of the constellation, Leo, a subtle shift in infrared light pierced the void after journeying more than 100 years to reach us. It appeared as ordinary data at first, just another sequence in the endless flood of information captured by humanity's greatest observatory. Yet concealed within that light was a revelation that shattered expectations. A chemical imprint not born from stone, wind, or fire, but from the unmistakable signature of biology. The James Webb Space Telescope had uncovered a world so exquisitely tuned, so brimming with the prerequisites for life, that researchers arrived at a conclusion of profound confidence. This was no vague hint or distant hope, but a planet that stands as one of the most compelling candidates for habitability ever observed, one that may surpass Earth in its capacity to sustain thriving ecosystems. The discovery emerged silently from infrared observations during the planet's transit across its star. Starlight passing through the atmosphere absorbed certain wavelengths, etching a unique spectral pattern into the data. Initial findings revealed essential building blocks: water vapor, methane, carbon dioxide, each a vital clue, each pointing toward potential oceans and active chemistry. Then arrived the compound that ignited intense debate: a possible detection of dimethyl sulfide, a molecule produced on Earth exclusively by living processes, from phytoplankton blooming across vast seas. Though the signal demands further confirmation, its presence alongside other anomalies has driven statistical confidence to levels uncommon in exoplanet science, with alternative explanations struggling to account for the full spectrum. This world, designated K218b, circles a cool red dwarf star 120 light-years distant, positioned precisely within the zone where liquid water can persist on a surface. Yet it defies the classic image of habitability, belonging instead to the intriguing category of hycean planets, larger than Earth, enveloped in a deep hydrogen-helium atmosphere, potentially hiding a global ocean beneath hazy clouds. Far from rendering it uninhabitable, this configuration may create conditions superior to our own. Surface temperatures appear moderated to a range ideal for liquid water, neither scorching nor frozen, sustained by the greenhouse effect of its thick atmospheric blanket. This blanket distributes heat with remarkable efficiency, smoothing out extremes that plague tidally locked worlds. The planet's greater mass, roughly 8 times that of Earth, generates surface gravity about 2.5 times stronger, firmly anchoring its atmosphere against escape. Where thinner worlds like Mars bled their air into space over eons, K2-18b retains its envelope securely, fostering long-term stability. The red dwarf host, dimmer and longer lived than our Sun, promises habitable conditions enduring for trillions of years, offering biology an almost eternal canvas for development. Orbiting every 33 days, the planet receives stellar energy comparable to Earth's, yet filtered through its dense atmosphere, which shields against flares while maintaining equitable warmth across day and night sides. What distinguishes this discovery is the atmosphere's profound chemical disequilibrium. Methane and carbon dioxide coexist in abundances that abiotic processes should rapidly deplete, yet they persist vigorously. On Earth, such imbalance is sustained solely by continuous biological input, organisms releasing gases faster than chemistry can erase them. K2-18b mirrors this pattern strikingly, with depleted ammonia further suggesting active removal, possibly by oceanic life. The potential dimethyl sulfide signal amplifies this narrative. If biological, it implies not sporadic activity but widespread production, perhaps from phytoplankton analogues flourishing in sunlit upper oceans. This is not a barren world awaiting life's spark. It is one where chemistry appears dynamically shaped by living systems on a planetary scale. Traditional searches for life demanded near-perfect Earth analogues, rocky, temperate, orbiting sun-like stars with thin atmospheres. K218b upends that paradigm entirely. It is no twin but a bolder variant, massive, ocean-dominated, hydrogen-rich, once dismissed as too exotic for biology. Yet emerging models of hycean worlds paint them as exceptionally favorable, with vast liquid water reservoirs and stable climates enduring far longer than Earth's precarious equilibrium. Strong gravity prevents atmospheric loss. The thick envelope buffers radiation and equalizes temperatures. Global oceans provide boundless solvent for chemistry. Habitability, it now seems, thrives not in delicate poise but in robust, resilient architectures built for cosmic longevity. Beneath the hydrogen-helium veil of K218b may lie an ocean of staggering scale, potentially deeper than any terrestrial sea, spanning the entire globe without continents to interrupt it. This is no fragmented water world, but a true ocean planet, where liquid layers extend under pressure that stabilizes conditions for complex molecules. Dissolved gases could fuel diverse chemistries, from surface zones lit by reddened starlight to deeper realms energized by internal heat or atmospheric reactions. Life here would not scrape for resources along coastlines. It could proliferate through volumetric habitats, layering ecosystems in 3 dimensions, drawing energy from light, chemistry, or pressure gradients. Evolution in such abundance might accelerate, producing complexity on scales unimaginable in Earth's constrained oceans. The potential biosignature strength carries profound weight. Dimethyl sulfide degrades quickly under radiation, requiring constant replenishment to appear in transit spectra across 120 light-years. If biological, its detection demands not isolated microbes, but oceanic blooms dominating global chemistry. Life so prevalent that its metabolic byproducts permeate the atmosphere visibly from interstellar distances. This suggests a biosphere not nascent or fragile but mature and expansive, where biology has imprinted itself indelibly on the planet's identity. The atmosphere functions less as passive cover and more as extension of a living system, cycling compounds in perpetual defiance of equilibrium. This single world reshapes galactic demographics. Red dwarfs constitute 3/4 of Milky Way stars, many hosting super-Earths to mini-Neptunes in extended habitable zones. If hycean configurations prove common, and early statistics suggest they are, then habitable oceans may outnumber rocky surfaces by orders of magnitude. Worlds once marginalized as gas-shrouded oddities emerge as prime life-bearing candidates, stable for trillions of years, while sun-like systems face eventual stellar demise. Life may not cluster around rare Earth analogues. It may abound on these larger, wetter, more enduring planets, maturing through epochs denied to our fleeting solar system. Hydrogen-rich atmospheres, long viewed as barriers to habitability, now reveal themselves as enablers. Lightweight yet massive in total, they trap heat superbly, erasing temperature swings and creating uniform climates. Radiation reaches the surface softened. Heat circulates globally. Extremes vanish. Biology faces no relentless adaptation to freeze or burn, but enjoys consistent comfort, freeing energy for growth, diversification, and sophistication. Hydrogen itself participates actively, dissolved in oceans, driving reactions, potentially serving as metabolic substrate independent of photosynthesis. Such worlds do not merely permit life, they cultivate it, transforming potential into proliferation. The observed chemistry narrates ongoing activity: carbon dioxide, methane, water vapor, and possible dimethyl sulfide form combinations unstable without renewal. Abiotic equilibrium remains perpetually deferred, as if invisible processes continually inject vitality. Earth's parallel is unmistakable. Photosynthetic and microbial cycles, pumping gases, sustaining disequilibrium against entropy. On K2-18b, the scale appears grander. concentrations implying not marginal biology, but planetary dominion, where life orchestrates atmospheric composition, like conductor of a vast orchestra. Every observed transit reinforces the portrait of a world alive in its very breath. Time emerges as the ultimate architect of complexity. Earth's 4.5 billion years yielded multicellular life only recently, interrupted by extinctions and upheavals. K218b's red dwarf grants trillions of years of steady illumination, with habitable conditions potentially persisting since early formation. Evolution here faces no impending stellar expansion or atmospheric freeze. It proceeds unhurried, exploring branches pruned prematurely on Earth. Given billions of years already elapsed, any biosphere may have achieved maturity far beyond our own. Ecosystems refined, chemical cycles optimized, complexity layered through ocean and sky. This detection signals a pivotal shift in human inquiry. The question evolves from whether life exists elsewhere to how abundantly it flourishes under diverse architectures. K218b demonstrates that habitability spans broader parameters than imagined: larger sizes, thicker atmospheres, cooler stars, deeper oceans. Ingredients, water, energy, stability, time, prove widespread, suggesting life arises readily where physics permits persistence. Webb has not only identified a prime candidate, it has illuminated a cosmos potentially teeming with living oceans hidden beneath hydrogen skies. One profound insight is that life on such worlds may thrive precisely because of conditions once deemed prohibitive. Earth's habitability feels contingent, vulnerable to ice ages, impacts, greenhouse runaways. Hycean planets appear collaborative. Thick atmospheres shield and warm. Gravity secures. Oceans buffer. Energy flows accessibly. Stellar, chemical, geothermal, reducing scarcity that constrains earthly evolution. Biospheres could extend beyond sunlit layers, tapping hydrogen-driven metabolisms in perpetual darkness. Life does not merely endure. It expands to occupy every viable stratum, from cloud decks to abyssal depths. With extended timescales, evolutionary outcomes diverge dramatically. Uninterrupted by mass extinctions or stellar threats, development could yield intricacies Earth has yet to approach. Vast symbiotic networks, planet-scale biological feedbacks, intelligences emerging from oceanic rather than terrestrial roots. If life ignited early and abundant water plus organic delivery make that plausible, then K218b's biosphere may represent not infancy, but advanced equilibrium, systems honed over billions more years than ours. Earth-like once implied superficial resemblance. K218b compels deeper criteria: persistent liquid water, stable energy input, atmospheric retention, biological regulation of chemistry. By these measures, hycean worlds may prove more reliably habitable, evading Earth's multiple points of failure. Our planet appears increasingly as outlier, fragile, transient, while massive ocean worlds emerge as the galaxy's enduring norm. Most life, if common, may inhabit environments alien, yet optimized, challenging anthropocentric assumptions profoundly. Webb's observations mark transition from speculation to empirical exploration. Where once probabilities and models dominated, direct atmospheric characterization now reveals tangible worlds with water, disequilibrium, potential biosignatures. Confidence grows not from single molecules, but converging evidence, composition, temperature, stability, chemistry defying abiotic explanation. This capability heralds systematic survey. Dozens, hundreds of similar targets await scrutiny. The threshold is crossed. We catalog not just planets, but living possibilities. The apparent ease of habitability here unsettles deeply. Earth's balance seems precarious, a narrow survival window. K2-18b presents the inverse. Conditions converge naturally toward sustenance. Atmosphere thickens protectively. Oceans persist globally. Chemistry activates readily. Physics appears aligned to foster rather than hinder biology, suggesting life as inevitable outcome when stability endures. This world does not look exceptional. It resembles a standard template for cosmic vitality. Envisioning life on K2-18b evokes vastness beyond terrestrial intuition. Oceans hundreds of kilometers deep create layered realms, sunlit surface teeming with floating ecosystems, mid-layers harvesting chemical rain from above, profound depths fueled by planetary heat. Organisms might span scales from microbial mats to colossal drifters, metabolisms blending light, hydrogen, sulfur cycles. Biosignatures detected may originate not from thin surface film, but from integrated vertical biosphere. Its collective exhalations rising through atmosphere to imprint on starlight. Perhaps most humbling is temporal perspective. K2-18b may host a biosphere ancient by Earth standards, evolved through eras we can only model. Red dwarfs form early, super-Earths accrete quickly, oceans condense soon after. Life could have arisen billions of years ahead, progressing through stages while Earth's surface remained molten. What reaches us now may be signature of mature ecology, efficient, balanced, fully integrated with planetary systems. We arrive not at origin but at ongoing symphony billions of years in performance. A mature biosphere implies different dynamics, not explosive growth but steady state, recycling perfected, waste minimized. Atmospheric gases maintained at precise levels by feedback loops, refined over eons. Dimethyl sulfide, if present, would reflect not erratic blooms, but calibrated production within global equilibrium. This is life not struggling, but sovereign, having solved long-term coexistence with its world. Throughout history, the cosmos appeared immense, yet barren. Exoplanet discoveries shifted probabilities, yet life remained theoretical. K2-18b alters that perception irrevocably. Space between stars feels populated with possibility. Worlds wrapped in habitable oceans, atmospheres bearing biological fingerprints. 120 light-years shrinks to conversational distance when chemistry travels as light. The universe reveals itself not empty, but enriched, structured by processes that readily produce living systems. What Webb has unveiled transcends one planet. It exposes a broader paradigm where habitability flourishes in forms we once overlooked. K2-18b stands not as fragile outlier, but as exemplar of resilience. Atmosphere active, oceans enduring, chemistry animated by life. Nature requires no mimicry of Earth to generate vitality. It needs only enduring conditions, and the galaxy supplies them lavishly. Humanity once gazed upward seeking kinship in familiar forms. Instead, we encounter something grander. Worlds superior in stability, richer in water, longer in duration. Reminders that life adapts, persists, transforms environments to its design. This era begins not with proof absolute, but with evidence compelling, tools sufficient, targets abundant. We read distant atmospheres and discern biology's handiwork across the void. K2-18b declares that when physics aligns toward persistence, the cosmos fills with life. Ocean worlds breathing beneath alien skies, evolving through time we scarcely comprehend, waiting not for discovery, but for recognition. If this vision has stirred wonder within you, reshaped your sense of solitude beneath the stars, pause to contemplate its meaning deeply. Share these revelations with those around you. Discuss what it implies for our place among living worlds, and join in the ongoing exploration of a universe far more alive than we ever dared imagine. For now, every distant point of light poses not the old question of loneliness, but the new one of abundance. How many oceans teem out there? how many biospheres breathe, and how profoundly connected we may yet prove to be.